Slope fields are historically a relatively new mathematical topic, but it has a lot of applications when we're talking about differential equations, particularly when we're trying to figure out the solutions to differential equations. So we're going to look at a slope field today, and also how to find the particular solution to that slope field. So we are given the differential equation dy dx is equal to x squared times y minus 1, and with that we want to sketch a slope field on the provided axes below. Now, a slope field is also called a direction field, and that is because we are actually not graphing a function, but we are actually sketching the slope of the original function, which would be the solution, at all these different points on the graph. So what I like to do is start with the easiest slope. The easiest slope to deal with is where the slope is equal to 0. So looking at my differential equation dy dx, I want to figure out, okay, well, what values for x and what values of y would make dy dx equal 0? Well, looking at that, if x is equal to 0, that entire equation dy dx would equal 0. So everywhere along x is equal to 0, I know that I'm going to have to graph a slope of 0. So a slope of 0, remember, is a horizontal line. So at every point along x equals 0, I'm just graphing little teeny tiny tangent lines that have a slope of 0. So these would be the tangent line to the original solution curve, which would be y, but we don't have that, of course. So that's the same thing as y equals f of x. Now going back to dy dx, there's another place where dy dx would equal 0, and that is when y is equal to 1. So all along y is equal to 1, I know I'm going to have to graph slopes of 0. So I'm going to graph little horizontal lines that have a slope of 0 all along y equals 1. So that takes care of 6 of my 12 points already, which is great. That's half my work. Now I just need to figure out, okay, what would be the slopes at the remaining points on this graph? So now I just need to pick a point, and we're actually going to plug in the x and y coordinate into dy dx to find out the slope value. Because remember, dy dx, by definition, is the slope of the tangent line. So let's just say I'm starting with this point right here. Well, at that point, x is negative 1, y is 0. So if I go up to dy dx and plug in negative 1 comma 0, I have negative 1 squared is 1, and then 0 minus 1 is negative 1. That tells me that dy dx would equal negative 1. So what I'm going to do is I'm going to sketch a line that looks like it has a slope of negative 1. Then I'm going to do the same thing with the next point. So here's my next point. So I have negative 1 is x, 2 is y, and so I have negative 1 squared is 1, 2 minus 1 is 1, so that gives me a slope, or a dy dx value, of positive 1. So I'm just going to sketch a line that has a slope of positive 1. Then at negative 1 comma 3, I have negative 1 squared is 1, 3 minus 1 is 2, that gives me a slope of 2. So I just need to make sure when I'm sketching it that it has a slope that looks steeper than the line that's below it, because that slope right here was a slope of 1. This needs to look like it has a slope of 2. So then if I go back over here, now I have x is 1, y is 0. Well, if I plug that in, I'm going to have 1 times negative 1 gives me a slope of negative 1. So that needs to match the other side, where the slope was negative 1 over here. Then I have 1 comma 2, so that gives me 1 times 1 is 1. So again, needs to make sure that it matches with the other side, which has a slope of 1. And 1 comma 3 would give me 1 times 2, which is 2. So make sure that it just corresponds with the slope that's on the left over there. So here's my slope field at the 12 points indicated on this xy plane. So now if I move this up, the next step says, while the slope field is drawn at only the points given above, it is actually defined at every point in the xy plane. Describe all the points in this Cartesian plane where the slopes are positive. Remember, the Cartesian plane is the xy plane. So what this is telling me is, even though I only have slope lines drawn where I have the 12 points here, it's actually defined everywhere on the graph. And so that means everywhere for every x and y value, I can draw a little slope line. So if I'm trying to describe all the points in the Cartesian plane where the slopes are positive, then I need to look at this graph and try to figure out, okay, what's the pattern of why are these points positive and the others are not? And then once I figure out that pattern, then that would be my answer for that question. So looking at this slope field, I have slopes of 0 at this T-shaped part in the middle, so I'm going to ignore those. Negative slopes on the ends here, so I don't look at those. The only place where I have positive slopes would be in this little corner and this little corner. So I want to figure out, okay, what do these 4 points all have in common? And that will be the description of where all the slopes are going to be positive on this Cartesian plane. Well, notice everything is above y is equal to 1, and it doesn't include where x is equal to 0. So that's going to be my description here. So if I move this back up, if I'm trying to describe where all the slopes are positive, well, based on the graph, that is where y is greater than 1 and x does not equal 0. Now, a lot of times when we are looking at slope fields, we use those to help us figure out the shape of the graph for the particular solution, or even the general solution, just a solution to the differential equation. A solution being, of course, the original function, y equals f of x. Now, if you kind of think of it like connecting the dots, let's say you have your slope field that has all your different lines, and it looks something like this. This one does not, of course. We already know what this graph looks like. But if I was to actually trace through and kind of connect the dots here, the curve that I could get by tracing and following along the slope lines would be what we call the solution curve. And so what we're really interested in is trying to figure out what is the particular solution, and we're going to do that by actually using integration. So for the problem we are working on, we had dy dx was given as x squared times y minus 1. And this question says, find the particular solution, y equals f of x, to the differential equation, dy dx, given the initial condition f of 0 is equal to 2. So really, this is asking me to integrate this differential equation to go back to the original function, and then actually figure out what the constant plus c would be when I plug in the point f of 0 is equal to 2. So first step, when I'm trying to integrate this, I have to always begin my problem by separating the variables, which means I'm going to put all the y's on the left, x's on the right. So I can divide the y minus 1 over and multiply the dx over. This allows me then to integrate on the next step because now the notation is already set up where I have the dy and I have the dx with that integrand already provided for me. So now I can integrate the left-hand side. Well, the left-hand side here is going to have to be a u subproblem. So my u would equal y minus 1, du equals dy. So then if I rewrite it, we have the integral of du over u, which goes back to ln absolute value of u. Now I'm going to have to move this up because I have to write a lot with this. So I have ln absolute value of u, which is y minus 1, is equal to, now I need to bring down the antiderivative for x squared, which goes to x cubed over 3, plus our constant c. Now, you may wonder why I put the plus c with the x side, but not on the left-hand side. Technically, you have a plus c over on the left, but because it's an unknown constant, just the general term, if I move it over, it'll just combine with this unknown constant over here. And so there's no purpose in having it on both sides when it would just move over anyway when you're eventually going to solve for y. So you might as well just put it on the right-hand side as the combination of the two constants for the general term there. Now, the question said we need to find y is equal to f of x. What that really is saying in terms of words is I have to actually solve for this y. However, before I isolate y, I really need to go ahead and find this c value because it'll just make it easier later on down the road, so I don't have to algebraically go back and find c after I isolate y. So basically, after you take the integral of both sides, go ahead and plug in your initial condition, and for your x and y, find your c value, then work towards isolating your y. So the initial condition that they told me I had was they said we had f of 0 was equal to 2. So right here, I know x is 0, y is 2. I'm going to go back and plug that in. and I have ln absolute value of 2 minus 1 equals 0 cubed is just 0 plus c. So this gives me ln of 1, which is equal to 0, which would equal my c value. So in this case, it doesn't really matter that much because c ended up being 0. But if that had been a different number, of course, I'd have to carry it through with all the following steps. So if I rewrite this, we have ln absolute value of y minus 1 is equal to x cubed over 3 plus c, which is now 0. And now that I have my c value already calculated using the initial condition, now my next goal is to isolate y. So to get rid of ln, we're going to raise each side to a power with e as a base. That'll allow me to cancel out the e to the ln. Then I'm left with the absolute value of y minus 1 equals e to the x cubed over 3. Now in order to drop the absolute value, we have to put plus or minus on the other side of the equation. So y minus 1 is equal to plus or minus e to the x cubed over 3. But here's the thing. My initial condition said that I had f of 0 was equal to 2. A particular solution, which is what we're trying to find, can only have one answer. That is why it's called a particular solution. There's only one particular answer with one initial condition. But when I put in that plus or minus, technically now I have two different equations. And so to figure out if it's the positive or negative version of this equation, I go back and look at my point and see, well, where is that actually located on the graph? Well, this is the point 0, 2. The y value is positive, which means I'm going to keep the positive version of this equation. So I'm going to drop the plus or minus and only keep the positive version, since my y value has to be positive based on the initial condition that we're using to find the particular solution. Then the final step is just add your 1 to the other side. So y would equal e to the x cubed over 3 plus 1. And that is my particular solution that goes through the initial condition f of 0 is equal to 2. So if I went back to my slope field, now that I know what the particular solution looks like, I can look and see, well, what would that actually look like on this graph? So if I follow the direction of the slope field, we have a slope of 0, then in this little area it has to have positive slope, but then we hit a slope of 0 once we get to the point 0, 2, and then it goes back to having positive slope. So I know the particular solution has to go through the point 0, 2. Other than that, I'm not sure exactly where the points are. That's why this is just a sketch. So I know I'm going to start down here at y equals 1, have it increase up towards that point, but then it kind of levels off and has a slope of 0 at 0, 2, and then it's going to increase some more with positive slopes after that. You're not trying to make it go through the lines, so like I don't need to hit this line right here. It's just all about the direction the curve is going. That's the whole point of the slope field, is so we can see what the solution curve would look like. So this is what y, which is f of x, would look like just based off of this differential equation, which we then found the actual solution by using integration. So here is the actual solution curve graphed out so we can see it nice and beautifully. So you can see it levels off at y equals 1, increases with positive slope, levels off with a slope of 0 at x equals 0, and then increases with a positive slope from there. And notice here's where you really get that exponential function when we had the e to the x cubed over 3. So thank you for watching, and hopefully that helps you out with slope fields and particular solutions.